All right, good morning, everybody. Hope you're enjoying reInvent so far. Welcome to today's DAT205 session. The title of the session, How Verizon Media Implemented Push Notifications Using Amazon DynamoDB. My name's John McCammett. I'm a Senior Customer Solutions Delivery Manager, and I'm with AWS. I'm joined here by Sunil Joshi, Senior Technical Account Manager, also with AWS, Bob Liano, Senior Principal Software Engineer with Verizon Media, and Harshal Shukla, Senior Software Engineer with Verizon Media. We're pleased to have the team with us here today. We've been working together for the last few years, and they'll be providing an in-depth discussion of how they've leveraged AWS to deliver services to millions of Verizon Media customers. So for our agenda today, we'll go through a brief overview of Amazon DynamoDB, review Amazon DynamoDB global tables and Amazon DynamoDB Streams, a brief overview of both of those features, describe the overall Verizon Media architecture, the solution that was developed to enable mobile push notifications, dive into the architecture that was deployed, and discuss lessons learned, and then some results delivered by the team. And I need to go the right direction here. So first, let's talk a little bit about NoSQL databases and Amazon DynamoDB. So cloud application characteristics are very different from traditional applications, and users can very easily be in the millions. Data volumes can reach petabytes and exabytes in short order. Performance is often measured in milliseconds and microseconds. On average, the app serves millions of requests per second. On a big day, tens of millions of requests. The application variance demands that systems can scale up, out, and in to maintain the right cost profile. While developers have to have access, instant access, via a fully managed API. The growth of internet scale applications, such as e-commerce and social media, the explosion of connected devices, such as smartphones and tablets, and big data have resulted in new workloads that traditional relational databases are not well suited to actually handle. Scaling an RDBMS to handle concurrency while maintaining strong consistency require upgrading to more powerful and often more proprietary and costly hardware. This is called scaling up or vertical scaling, and it usually carries extremely high cost. NoSQL databases like Amazon DynamoDB address the scaling and performance requirements and challenges found in relational databases. NoSQL databases trade some of the query capabilities and ACID properties of an RDBMS for a much more flexible data model that scales horizontally. These characteristics make NoSQL databases an excellent choice in a situation where use of an RDBMS for non-relational workloads is resulting in some combination of performance bottlenecks, operational complexity, and rising costs. DynamoDB offers solutions to all these problems as an excellent platform for migrating these workloads away from an RDBMS. Amazon DynamoDB is a fully managed NoSQL database in the AWS cloud. The complexity of running a massively scalable distributed NoSQL database is managed by the service itself, allowing software developers to focus on building applications rather than managing infrastructure. NoSQL databases are designed for scale, but their architectures are sophisticated. And this can have significant operational overhead and running a large NoSQL database cluster. Instead of having to become an expert in advanced distributed computing concepts, the developer need only to learn DynamoDB's straightforward API using the SDK for their programming language of choice. In addition to being easy to use, it's also cost-effective. With DynamoDB, you pay for the storage you're consuming and the I/O throughput that you actually require and have provisioned. It's designed to scale elastically while maintaining high performance. When the storage and throughput requirements of an application are low, only a small amount of actual I/O throughput is deployed to DynamoDB. As the number of users of an application grows and the required I/O throughput increases, additional capacity can be provisioned on the fly. This enables the application to seamlessly grow to support millions of users through thousands of concurrent transactions. Finally, DynamoDB is extremely secure, with support for end-to-end encryption and fine-grained access control. So we're going to dive into a couple of the key features here of DynamoDB. And so now Sunil will drive some of these discussions around Amazon DynamoDB capabilities. Sunil?
Thanks, John. I'll be giving you a little bit of background on global tables and DynamoDB Streams, two key services that are used in the push notification platform, which is the topic of the discussion today. Also, I'll give a sneak preview on the new version of DynamoDB global tables that was just announced. And secondly, I'll talk about an example design pattern using DynamoDB Streams. DynamoDB already has a global footprint. The global tables leverages that, and it provides fully managed multi-region, multi-master database that provides you with a fast local read and write performance for your massively scaled global applications. Global tables replicate the DynamoDB tables across AWS regions of your choice. This relieves you from the difficult work of replicating data and resolving conflicts, thus enabling you to focus on your application's business logic. Global tables also allows your applications to stay highly available in the unlikely event of isolation or degradation of an entire region. A new version of global tables was launched recently, and you can now actually display the version you are using the AWS console. For example, for this new version, you will see the version string 2019-11-21. For any tables created prior to that date, the version string will start with 2017. Some of the features in this new versions are relevant to the customer's case study. Therefore, I thought I would share with you some of these new features. You can now convert existing single region tables to global tables. This enables you to easily create a hot standby for disaster recovery purposes. You can also extend your tables to additional AWS regions for fast local performance, especially for low latency applications. You can add new regions to your existing global tables at any time. Your applications can continue to write to the existing regions while DynamoDB creates a new replica in the background, and all the in-flight upgrades will eventually be replicated to the new replica. Secondly, you will see a faster and less expensive replication between regions. This is because we have simplified our internal mechanisms for data replication. Previously, we added 3 attributes to the item, which resulted in an additional write into the region. These attributes were added to your region, to your schema, for synchronization purposes. Now we natively manage the replication. So as a result, only one write happens in each region of your global table. As a result, you will see up to a 50% reduction in cost for your global tables as compared to the previous version. If you created global tables prior to November 21st of this year, an upgrade tool will be available in a few weeks that will let you convert your existing global tables to this new version so that you can make use of the new features that I just talked about. Next, I'm going to talk about the design pattern for DynamoDB Streams. So when you build solutions using DynamoDB, sometimes there are requirements to synchronize item-level modifications as they happen in near real time. You may want to notify other users or other systems when these changes occur. You may want to audit or archive these changes. Sometimes you may want to replicate data to other data stores. You may have to do some computations for building aggregates of your existing fields and write them back into the table. And finally, you may want to build a search engine for the data stored in DynamoDB. For all these use cases, DynamoDB Streams is a powerful service that you should consider while designing your application. DynamoDB Streams captures a time-ordered sequence of item-level modifications and stores this information for 24 hours. Applications access these in the form of stream records in real time. Now, when you build your streams processing layer in your application, there are 2 options. You can use Lambda, which is serverless. The advantage with Lambda is you don't have to manage any infrastructure. Alternatively, you can build a custom app using Kinesis client library and what is called as DynamoDB Streams adapter and host it in an EC2 instance. So why would you want to build an app and have a static EC2 instance for your stream processing? Well, there might be cases where your application requires more sophisticated record processing, or you may want to have more control over the behavior of your application. For high-velocity streams processing, having an EC2 instance may be more economical than using Lambda. In the use case that Verizon Media team is going to share shortly, they chose to develop the app using KCL and DynamoDB Streams Kinesis adapter. As you can see in the diagram, their use case is to replicate data to synchronize with item-level modifications and build a custom search engine. Now, there are a couple of things to note while you develop your app using KCL. You need to manage and monitor the shards. You have to manage the checkpointing process, and you're responsible for scaling of the KCL workers. You may need to host the custom app in an EC2 auto-scaling group for high availability. Finally, there are a few key configuration parameters of the KCL workers that you will need to tune for optimal performance. Now, the Verizon Media team is going to demystify all this and share their insights coming up shortly here. So I'm going to give a quick introduction into the customer. As a background, Verizon Media is a subsidiary of Verizon. It was formed 2 years ago with Verizon's merger of AOL and Yahoo. And it's now a media and technology brands powerhouse with brands such as Huffington Post, Verizon Digital Media Services, Yahoo Mail, Yahoo Finance, Yahoo Sports, and dozens of others. Verizon Media connects with 1 billion people around the world. It reaches more than 2 billion mobile devices and leverages more than 4 trillion data points every month. Verizon Media has had a long-standing relationship with AWS. AWS is home to many of Verizon Media's marquee web properties, and Verizon Media runs key segments of its advertising business on AWS. About 2 years ago, the Verizon team here started to work on a better, stronger, and faster push notification platform that is used by many of the iconic brands that you all know and use every day. AWS and the Verizon team iterated through different architecture options and finally settled on Amazon DynamoDB, SQS, and ElastiCache as their basic building blocks. Now, here to talk about the whole journey is Bob Liano, Senior Principal Engineer from Verizon Media.
Thanks, Anil. So the journey started by endless meetings, requirements gathering, talking to all the brands. And it was very, very clear that push notification is the most effective way to bring stories to our users in a timely fashion. Hands down, there is no other mechanism that's more effective than push notification. So therefore, we had 3 things in our minds. We need to make a better, stronger, and faster push notification platform. What is better? Better means that we better be first to your lock screen. Your lock screen is a very important piece of real estate in your phone. We want to be first in there. We want to be timely, and we want to be accurate. So because we need to be better, we also need to be stronger. The brands told us breaking news happens at any time. You cannot predict this. Therefore, once a push notification must be triggered, our platform must be ready. There is no downtime. There is no cold start. You cannot make any excuses. Faster. We have a goal of 27 million devices in 3 minutes or less. We need to complete the 27 million push notifications in that time. So all of these better, stronger, faster applies to each of these brands that you know and love, hopefully, and make it your daily habit. Each of these brands are expecting the better, stronger, faster. And the additional challenge there is that there is what we call this perfect storm, where all these brands trigger a push notification at the exact same time. So our promise to them is they won't even feel that. They won't even know that there should be no additional latency in their push notification completion times. So our selection process for the technology, we talked to our AWS colleagues, and we said we need to use the battle-tested services here. DynamoDB, DynamoDB Stream, simple queue service, and sure enough, they delivered. It's really very reliable. It just works. So what's the use cases? Top of mind use cases of our brands over and over again, content-based push notification. This really means that editors must be very, very comfortable and easy to say, hey, I've got a piece of article. I need to push this article to 8 million devices, for example, as a user base. It should be so easy to do this. They just send us a string We match the string to all the devices that are associated with that string. Let's say hashtag breaking news. The second requirement was personalized push notification. So if you're a user of our apps, you can make a comment to one of the articles, and then someone else can reply to your article or like your article, and that triggers a push notification back to the original commenter. This creates a good community, right? You're interacting with other users. This gives you a warm and fuzzy feeling about your interaction with the rest of the world. The third is multi-criteria. Our editors really, really need an easy way to target push notifications to segments of users. So in this example, we gave them a feature that they can target push notification to iOS 13 devices in the US Eastern time zone. It's so flexible. And the fourth is throttling. We are very, very conscious of not spamming push notification to our users. Therefore, we afforded our brands a mechanism to control the push notification pace or rates. Engineering-wise, we had a team of 4 people that started this journey, and we were very clear on our requirements. We are obsessed with speed. That means we are working towards 150,000 devices to be completed in 1 second or better. The nature of push notification is that it's very bursty. So when breaking news happens, we have a flurry of push notification computation, and then after that, some moments of idle, right? So when those moments of idle happen, we should not be paying for those resources. It's a waste. So our finance guys are on top of us and saying, hey, we monitor your CPU or compute usage, and we need to optimize this. We settled on an asynchronous event-based architecture. There is just no way that microservice A makes a blocking call to microservice B. We need to make sure that we're using an event-based architecture. SQS really delivered the goods. Amazon DynamoDB delivered the goods on this requirement. And of course, 24/7, 365. There is just an imperative that do whatever you can so that when a breaking news happens, and we need to push to our users because they need to get this information in a timely fashion, that your platform, our platform, is ready. There's just no excuses here. So we wrapped our microservices with health checks. We instrumented it up and down, left and right. We have alerting systems. We learned 2 things. One is we need to know the health of the system, and second is we need to know if the system is failing before it fails. That's really critical learning experience for us. That should give us time to make some recovery mechanisms. So let me just deep dive into the architecture. We have a data management flow. Obviously, we need the device token or registration token from the device to flow into our platform. That is being done through the registration API. The association API is the way for mobile applications to tell us their users. The mobile application brands have the complete flexibility to identify their users. We have no say in that. It's really very flexible. Thirdly is the subscription API. This is the way by which the mobile applications can tell us that if this user is subscribed to breaking news, or is this user subscribed to Golden State Warriors. So all this information flows into DynamoDB. And we need to flow that information to our Verizon Media Vespa search engine. And to do that, we used the DynamoDB Stream. Just a quick example of the data model. So you'll see here the registration object. Most important, the highlighted in red is this push info.push token. This is the registration or device token required by Apple Push Service or the Firebase Cloud Messaging. This is the only addressable entity that they can recognize so they can send a push alert to their devices. Association object, this is a finance user with that ID. The subscription object model, here the example is there's two tickers, Verizon and Amazon. So if there's news about a price uptick or a downtick, we can perform a push notification on those events. The second major flow is actually the push notification itself. So we have a publish API surface. There's two important pieces here. The editor must specify the payload section that contains the title, the body, any emojis in this body, and also any metadata that is required by the mobile application as it gets the push notification. The second key piece of information is the query section. This is the way by which the editor can specify, hey, I want to target this push notification to #breaking news, or to signed-in users, or to signed-up users, or to users that are subscribed to your favorite sports teams. So the publish API packages these two things and puts it in an SQS message, which is the Search Planner SQS. Now, we have two services, Search Planner and Search. These two services, all they need to do is to get all the devices that match that query section. That's their responsibility. We have a fleet of these services that gather all this information. So as the response comes back from the search engine, it comes back in the form of a document. Every document represents a device. So giving you an example, 8 million devices, for instance, that's around 32,000 SQS messages that will be deposited to our delivery SQS. Why 32,000? We capped each SQS message to 100 kilobytes. So that's around 200 to 300 device objects, and plus the payload section. So it turns around, and we have the delivery service reading from this delivery SQS. There's 150 reader threads for every delivery service process, and there's a long poll of 10 seconds, and we ask for up to 10 messages. So an SQS message gets sent to the receiver or to the listener thread, and that listener thread goes and dispatches that to an executor service internally, because we need to parallel for loop through all these device objects. Now, since SQS is at least once, there will be moments where we will get two SQS messages that are exactly the same piece of data. So we need to always perform a deduplication. And the way to do that is we use Elasticache for Redis. Really, really very powerful. The command that we used is set NX. We gave it a key. That's the registration or device token, and a unique identifier for the publish request. So after we dedupe, we only have the unique device objects. The delivery service then makes an HTTP request to Apple Push Service or Firebase. It then gives us a status code, pass or fail. We package that status code along with the device object information, ship that off to our analytics. On the other side of the analytics is someone or something that's going to analyze and evaluate how effective this push notification request was. Effective in means of, if the users opened the push notification toast and went to the proper place in the application. Horizontal scaling. So what we did was we have C54X large machines, and we stacked up containers in each of the C54X large. We used Kubernetes horizontal pod autoscaler to horizontally scale. It's also very effective to decommission the EC2 instances and the containers once the burst is finished. This is the way we addressed our finance guys. Hey, we're not going to ever pay for idle. So this was a very effective way of fulfilling that requirement. Some facts and figures on Amazon SQS .send message. We did not use the send message batch. We were happy with send message. The maximum size for our Amazon SQS message was capped at 100 kilobytes. That's around 300 messages, 204 to 300 device objects. We enabled the custom retry policy. We had no back off, and we had a total retry attempts of 3. So it's the SDK that's doing this, not our application anymore, if you enable this custom retry policy. We use gzip. Our max connections is 10,000. We connected that much to SQS for every Java process. And we have a connection timeout of 100 milliseconds. In our testing, this was the magic number. So the request timeout, here's really interesting, is from the point of view of the publish API to deposit SQS message into the search planner SQS, we only allowed 300 milliseconds for a request timeout. We need to free up the web server threads really quickly. But on the internal ones, it's up to 2 seconds, or excuse me, 2 minutes. So let's look at facts on the performance. We reached up to 1.8K TPS. The P95 was 684 milliseconds. The size of the SQS message has an influence on the latency of the Amazon SQS .send message. So the bigger the message, the longer it takes for SQS to return with the status code. Now on the receive side, we have every JVM, every delivery service has 150 threads that call the Amazon SQS .receive message. Magic number, long hold time was 10 seconds, and we asked for 10 messages, or up to 10 messages per receive message. A great discovery was SQS does not load balance really quickly. In other words, when we horizontal scale, there will be new receive connections to SQS. And we would notice that, hey, it only returns 1 message. So it'll be better as the milliseconds go along. It'll be more distributed. So the next speaker, Harshil, will talk to you about Amazon DynamoDB and DynamoDB Stream. Thank you.
So thank you, Bob, for the great details on the notification service and SQS. For remaining of the session, I will talk on how we use DynamoDB and DynamoDB Stream, and also what makes them the critical component in our system. DynamoDB is a primary source of truth for us. We have customer-facing APIs to get user registration, subscription, and other information. This API then stores this data synchronously into respective DynamoDB table. This API traffic is very bursty, so we needed DynamoDB to scale accordingly. Initially, we started with the provisioning throughput, which comes with the auto scaling. But we noticed that DynamoDB does take some time to auto scale, which won't work great with our busty nature of traffic. So we decided to use on demand. On demand works really well if you have an unpredictable traffic pattern, and that is the case for us. The second interesting thing is global tables. High availability is another main component for our application. So we decided to use 2 regions, US East 1 and US West 2. US East 1 is our primary region, where all of our API traffic happens against that. So we needed a mechanism to auto-replicate data across our different regions. DynamoDB global tables lets you do that. Using DynamoDB global tables, we auto-replicate our data across different regions and keep all our regions' data in synchronous. So that way, in the case of region-specific issues or outages, we can easily BCP over to our secondary region and have our system up and running. One of our table registration, which holds user device information such as push token, language, region, timestamp, etc. This information is later on used for notification purpose. This table currently holds around 70 million records, which results into 200 GB storage wise. From the top right graph, you can see the write capacity units are ranging from 5,000 to 40,000. You can see how our API traffic is very busty here. The bottom graph shows the replication latency. Even with this busty traffic, the replication latency is staying around 1.2 seconds on an average. This table also has a DynamoDB stream enable with new and old images, which I will talk later on. Another important table is a subscription table. We store our user's subscription data into its own respective DynamoDB table. The storage-wise, this table is not as big as our previous table, but it currently holds data around 80 GB, and the number of record it has 300 millions. This table is one of the heavily accessed table in our system. From the top right graph, you can see how busty the traffic is for this table. Even with this sudden bustiness, the DynamoDB on demand scales really well for us. Here the write capacity units for these tables are ranging from 3,000 to 45,000. Even with this busty spikiness, the DynamoDB replication latency is still staying around 1.2 seconds on an average. That is really impressive for us. Same as our previous table, this table is also on demand, has a DynamoDB stream enable with new and old images. Along with these two major tables, we have many other small tables which helps our system to run. So you can imagine how heavily we are dependent on DynamoDB for our application. In the beginning, Sunil talked about DynamoDB Stream. So here I would like to share out how we consume data from DynamoDB Stream real time and store that into our search engine for later querying purpose. We have a search engine called Vespa, which is being used during the notification publish time to find out audiences based on a defined tag along with some complex criteria. So we needed a mechanism to consume data from DynamoDB and store that into our search engine. And that's where the DynamoDB stream comes in a picture. In DynamoDB, you have partition. DynamoDB stream has shards. This partition and shard has one-to-one mapping. Each shard in DynamoDB stream holds data for up to 4 hours. After that, it will be resharded. Once it gets resharded, you will get parent and child model. So if you want to consume data from children's shards, you have to first finish processing data from the parent shards. Currently, there are two ways you can consume data from DynamoDB stream. Either you can attach a lambda to it, or you can write down your own custom application using KCL and DynamoDB stream adapter. Our developer team loves this second option. Using this second option, you can initialize a consumer worker instance with just few lines of configuration. KCL will take care of abstracting out all the management logic for you so that you can simply focus on your core business logic. You still have an opportunity to play around with some tuning parameter to optimize your consumer. With this way, you can run your code on any machines, but you still have a full control to tune the parameters. DynamoDB stream has a insert, update and modify events. Since we have the global tables, we observe that each single write happening against our primary DynamoDB table, DynamoDB stream contains two events, actual insert and duplicate modify. This duplicate modify event is being used by AWS services to replicate that data in a different global tables. Basically, this duplicate modify event is useless for our application. So we have in a DynamoDB table, we have stored timestamp field. When this record comes back on the DynamoDB stream, we have a new and old image. By looking into this new and old image, we read the timestamp parameter. If the value for that parameter is the same, we consider that as a duplicate event and we do not process it and drop it on the floor. DynamoDB stream holds the data for up to 24 hours. After that, it will start dropping the records which are older than 24 hours. The application can become slower or the exception can also happen. So we wanted to handle this very nicely. So we decided to keep the fallback mechanism. For this fallback, we decided to use SQS. So whenever the exception or the failure occurs from our primary feeder, we write that message into the SQS. There is a service attached to that SQS which reads this failure message, goes to DynamoDB to get the latest snapshot and write that back to our search engine. This design also helps us in the case of our downstream system being slow. If our downstream system becomes slow from the primary feeder, we stop writing to that downstream system and we can write it to the SQS. That way, from your primary feeder, you can still consume the data from DynamoDB stream and do not worry about 24 hours retention time. This design helps us to efficiently consume stream records in real time and ingest that into our search engine within 1 or 2 seconds. Now let's talk about scaling DynamoDB stream consumer. Initially, we started with a single worker consumer. So it was working really fine for most of the time. Intermittently, we were experiencing some delay in the process. So we did a quite few rounds of optimization, but the feeder delay was keep popping up. Since the bottleneck was a single consumer, we decided to go with a multiple worker consumer topology. While talking to AWS support team, we came to know how simple it is to run the multiple worker consumer. The key here is to use a unique worker ID along with the same application stream name. As long as you have these two parameter covers, you can deploy the same exact code on any number of machines to increase more workers. And KCL will make sure to do the load balancing for you. So let's say if you deploy this code to multiple machines, KCL will make sure when the new worker comes up or the existing worker goes out, it will make sure to assign a lease of that shard to a proper worker. From the top right code snippet, you can see how we define the unique worker ID. For us, we decided to use a system timestamp of nanosecond and append it with the stream application name to achieve the single worker ID. The another key parameter here is with max records. So when you define an instance of a worker, you are allowed to define up to how many records you want to consume per batch. When KCL gives that messages, you can process them in a batch. The attribute that you can set is with max records. So now let's say if your consumer running super fast and you see a lot of messages sitting on the DynamoDB stream, right? So you can increase this value of the parameter to make your consumer run even faster. The second most important attribute is with failover time millis. When KCL gives a batch of record to a thread who holds the lease of it, by default, it gives 10 seconds to that thread to process all those messages. Now, if your application is performing slower and if you take longer than 10 seconds, KCL thinks that, hey, something has gone wrong, and it will take the lease from that thread and assign to another thread now. So the previous thread can continue processing it, but once it is done continue processing it and try to increment the checkpoint, KCL won't let it do it because now the lease has assigned to another thread. So that another thread need to process the same batch of record again. If you are experiencing the slowness, it is possible that you again gonna go over 10 seconds. If that happens, KCL will take the lease from the thread 2 and can give that another thread, let's say thread 3. If this continue happen, you gonna end up in a like the Dale loop. But the good thing about is you can tweak this parameter. For us, we moved to 20 seconds, which is working really fine. However, it is advised to not go over more than 50 or 60 seconds. Incrementing checkpoint too often can actually increases your latency and can slow down your consumer. So instead of incrementing too often, do it every 50th or 100th record. For us, incrementing at every 100 records is working really fine. So how does all these settings helps us in our feeder? With all the above settings that I just mentioned, our DynamoDB stream consumer search feeder, which reads data from DynamoDB using KCL and DynamoDB stream adapter, currently able to ingest around 55 million registration events and around 60 million subscription events per day per region. The bottom graph shows how we are doing per second level. This design currently helps us to achieve 3000 events per second per stream per region. You can also say that from the time a user subscribes something on their mobile app or a browser, that subscription will go into our final search engine via an API through DynamoDB and DynamoDB stream within 1 or 2 seconds. So it is guaranteed that that user will not miss the notification which is happening after 1 or 2 seconds. So let's talk about overall results to show how our notification system performs with using all these AWS services. In the beginning, we mentioned that our traffic is very busty. So we did not want to run our application at a full capacity 24/7. Instead, we want to rely on autoscaling. We use horizontal pod autoscaler for Kubernetes to autoscale our services during the burst of traffic. With AWS services like DynamoDB, DynamoDB Stream, and SQS, along with autoscaling, we can send notification to 150,000 devices per second. The architecture is very simple and easy to scale. With just few configuration change, our system can send notification to up to 500,000 devices without even doing any deployment. From the right side graph, you can see how nicely our system scales up and down during the burst of traffic. The bottom graph shows how our horizontal pod scales up our services. So here is a feedback from our internal team, Yahoo Fantasy, how our notification platform helped them to launch NFL draft notification, which is really critical and important for their fantasy users. They have a use case where their notification happens so close to their user's subscription call. So our design, which ingests the data within a couple of seconds, becomes really handful for them, and they are really happy with this design model. Now let's talk about some of the lessons that we learned over the time period. As we know, DynamoDB holds the data for 24 hours. Make sure you are able to consume before that. Your application can become slower, or the exception can also happen. So it is recommended to have the fallback mechanism in place. Our SQS-based fallback mechanism becomes so handy that we can easily switch back and forth when the downstream system is experiencing the delay to avoid the data retention period time. As we know that SQS can hold the data for up to 14 days. Incrementing the checkpoint is a really expensive operation. When you try to increment the checkpoint, it has to scan your DynamoDB stream table, which is really expensive. So don't do like every single time, do it periodically, or you can do like every 15th or 100th record. The another important thing here is when you are trying to increment the checkpoint, make sure you define the instance of the record up to which you are trying to increment the checkpoint. To give you an example, let's say you got 500 messages as part of the KCL fetch. Now after processing 100 records, you decided to increment the checkpoint without passing the instance of that record. KCL will think that you are trying to increment the checkpoint for all those 500 records. So if that call successfully executed and your service goes down, and when it comes back, KCL will give you the record from 501. So basically you are losing the data for those 400 records. So make sure you always pass the instance of the record up to which you are trying to increment the checkpoint. Handling the exception properly. When exception occurs, make sure you do not just swallow it. If you just swallow it, you will make your application to update the checkpoint and KCL will give you the new record. Same way, do not just throw the exception. Otherwise, KCL will think it as a failure and it will give you the same record again. So now let's consider if your record has malformed and if you are throwing the exception, it will make KCL to keep giving you the same record and you're going to keep throwing the exception. You can end up in a dead loop here. So make sure you do handle properly. One thing you can do here is, on the case of an exception or a failure, you can write down that to another fallback mechanism so that your primary feeder can continue incrementing the checkpoint and can keep reading the new messages. In the fallback mechanism, make sure you have a mechanism to handle the ordering because DynamoDB Stream was doing that for you. Now it's your job to do it. So one thing you can do here is, in your fallback mechanism, when you read the failure message, you can go to DynamoDB to grab the latest snapshot and then you can write that latest snapshot to your downstream system. Set with failover time millis and with max record attributes properly. Do proper testing when you modify these two attributes to make sure the number of records you get with max records are able to finish processing within the time defined in with failover time millis attribute. Otherwise, you're going to end up in a dead loop. When you create a global table, remember to select all the regions at the time of a global table creation. However, as Sunil described earlier, with the newer version of the global tables, now we are allowed to add additional regions to the existing global table clusters. DynamoDB provides eventual global consistency. And here we experience the replication latency around 1.2 seconds on an average. It is possible that the data will get replicated at a different rate for different DynamoDB table. So in your DynamoDB stream consumer, if you have a dependency for one stream to go and read the data from another DynamoDB table, it is possible that the data not being there in the another table when you go and read it. If you have this use case, one thing you can do is when you're trying to read the data from the another DynamoDB table, and if it is not there, you can write down that to your fallback mechanism. And from your fallback mechanism, you can retry that message X amount of time or until the data becomes available. And data won't become available after like 2 or 5 or 10 seconds. It usually becomes available within 1.2 or like less than 2 seconds. See if you can filter out the redundant modify events. By filtering out the redundant modify events, you can actually put a less load to your backend system. You can save the cost, and you can actually make your consumer run faster. But with the newer version of the global tables, now these duplicate modify events are also not getting returned into DynamoDB stream. So that's gonna helpful really well. So we don't have to worry about this use case anymore. Keep an eye on your DynamoDB stream application table. This table shows the shards count, and for each shard, it will tell you what is the lease attached to it and what is the checkpoint value is. If you see the shard with the checkpoint value as a trim horizon, that means that shard doesn't have any lease attached to it, and it has not even started processing. If you see too many shards with the checkpoint value as trim horizon, it means your worker is processing really slow. It's time to add more parallelism by adding more workers. Lastly, partnering closely with AWS team is really important. If you have a value-added service, use it. It's gonna really helpful. If you have any launch going on, make them aware of it. And if you have any critical launch coming up, invite them to your war room. You're gonna see the benefit of that one. And here is a quote from our VP of Engineering on our experience on AWS technologies. Now I will hand it over to John. Thank you.
All right, great. Thank you, Harshal. All right, so thanks for joining us today. You came here ultimately to reinvent to learn, right? So there's no need to stop when you go home today. Keep reinventing. There's a ton of AWS resources for training and certification, specifically for databases here. The option for databases is proliferating, ultimately leaving leaving customers to navigate a myriad of these options. And let us help, right? It's really important to let us help you. There is a new database overview course that provides a foundation in 4 hours. We offer videos and primers on 7 AWS database services, and then validate your experience with a certification. Obviously, we have certifications available too across the board. So with that, I want to thank you. I want to specifically thank Bob and Harshal for coming and joining us today and sharing their story with us. And if you have the time, please, of course, go into your app and rate the session. We always appreciate that. If there are additional questions, we'll be available after the session and happy to kind of dive into any more details, or if you do have more questions for us. So thank you and have a good reInvent.